Hi guys, for this particular video, and you'll have to bear with me, I've got a new camera that I'm working on now, so I'm just trialling this out, so hopefully it'll be fine. It is an extension to the last video that we did, and we're going to be we're going to do some more work now using our algebraic techniques to solve equations that involve natural logarithms. Now, on the previous video that I sent out to you, and I know it was quite a lengthy video because I wanted to give you a sort of bit of an insight into the importance of this Euler's number E, but also this idea of the natural logarithm and why it's important. And we're going to build on this now because there are a lot of models that we're going to use. We looked at a couple of them. We talked about exponential growth and decay models, so we're talking about things like population growth or radioactivity when we're thinking about exponential decay. So I just wanted to take this a little bit further. Again, we're going to be moving around now in the exercise, so the last video would allow you to have a look at exercise 14b. This will now be exercise 14g, but I'll remind you that towards the end. So we're going to be working with natural logarithms, but before I do that, I just want to remind us how it is useful to be able to use logarithms to help us solve equations where the unknown, the variable that we're looking for, that we're solving for, is an exponent or a power. So I'll just go through a couple of very quick examples. And when I'm doing all of these, we're going to be doing them and leaving our answers in exact form, rather than putting them in our calculator and getting our decimal answer and giving an approximation. We're going to be leaving it in exact form when we're doing these calculations. So the first one, just as a reminder, we're going to be solving things like this. 5 to the x equals 20. Now, here we can get a rough idea of what the answer is going to be, because 5 to the power 1 gives you an answer 5. 20 is clearly bigger than that. But 5 to the power 2, i.e. 5 squared, is 25. And we want 20. So our answer is going to be somewhere between 1 and 2. It's going to be a decimal between 1 and 2. Clearly 25 is closer to 20 than 5 is, so it's actually going to be a number here that's closer to 2 than it is to 1. So if we had a guesstimate at this stage, it could be about, and you could have a look in your calculator, about 1.6, 1.7, maybe in that sort of region, maybe even a little bit higher. Anyway, the way we solve equations like this is we take logs of both sides. So when I'm going to do this, I'm going to take log base 10 at the moment. I know we're looking at natural logs and we'll have a quick look at them and then a few examples, the ones that are in your notes, so that you can go back and look at them and fill in the notes as you're going along, and then you can have a go at this work and upload it onto Teams as well. But when I'm looking at an equation like this and I want to solve it, I take logs of both sides. Remember, we're balancing an equation, so as long as I take logs of the same base of both sides, then the equation will still be balanced. So I'm going to just write, when I'm solving an equation like this, I'm just going to take logs of both sides, which means I'm going to go log 5 to the x is equal to log 20. Now, if I don't write a base, remember from the previous video, that just means log base 10. By doing that, it allows me to bring this x down in front using the power rule, and it brings that x into play. So I'm going to do it, bring the x down, and we go x log 5 equals log 20. And then all I need to do to finish this is we need to divide by log 5, and we get x equals log 20 divided by log 5. Remember, log 20 is a number, log 5 is a number. This is the point where you could put it into a calculator and you can find out what the answer is and write it as a given number of decimal places. This is what I mean by my answers being left in exact form. I'm not actually going to go on and do that final bit of the calculation, because it's not important to this process that we're using here to solve equations. In this case, where the variable is unknown, all our equations will be of that form. But more specifically, when we're working with natural logarithms, there's a lot of equations, a lot of models, and we're going to do some more work next video, next lesson, where we're going to look specifically at models that involve this Euler's number here, E, as a in amongst the equation. But we're going to look at how we can use natural logarithms to help us solve and simplify them type of equations. You might get another equation something like this: 3 to the 4x plus 1 equals 50. And we want to solve this one for X, I can see X is a power here that I'm looking for. So as I did before, I just take logs of both sides. So I go log 3 to the 4x plus 1 equals log 50. I've taken the same log base 10 of both sides. The equation's still in balance. But by doing that, I can now bring this power into play in front. Now, we have looked at equations like this on a previous video. Just remember, when you're bringing this power down in front, we need to make sure we put brackets in. So the power 4x plus 1 log 3 equals log 50. So all I've done on this step is brought the power down. If I don't put brackets in, then this is actually saying 4x plus 1 times log 3. And I don't want that. What I actually want is to bring the power down multiplied by log 3. Both of them. So we just need to remember, if there's more than one term there that you're bringing down, then you need to put brackets around it. At this point, there are a few different ways we could go along and solve this. You could multiply this log 3 across the bracket and rearrange, or as I'm going to do here, I'm just going to divide by log 3, so I get 4x plus 1 equals log 50 divided by log 3. And then last couple of steps, I need to take the 1 over, so you get 4x is log 50 divided by log 3 minus 1. And finally, we need to divide everything by 4. There are a few different ways we can write this, but I'm just going to do it with a bracket because it makes it easier. So I'm going to find a quarter of, a nice square bracket there, log 50 over log 3 minus 1. So all I'm doing for that final step is getting the answer to this, and then I'm just dividing it by 4 or finding a quarter of it. So I just put a quarter there at the front. And again, I'm going to leave it in exact form. It's more the process that we're going through to get the answers rather than what the answers are for this particular lesson. Right, what I'm going to do now, let me take this off. This was more just a recap of the previous lesson. So let's have a look at this idea of natural logarithms. We mentioned it before. Apologies, I'm just going to get this off. Give myself this space to work with. And here we go. Apologies that it just takes a second to rub this off. Right, let's have a think about e to the x. We mentioned e to the x before. We said that e to the x, well, e basically is approximately equal to 2.718. We looked into this last time. That's the value of e. It's that special function whose derivative is equal to itself. And we've looked at differentiating e to the x. And the last video, the exercise that you did on the back of that, it had questions in which you were differentiating functions of the form e to the x or e to the ax, and there was a number in front of it. We did cover that briefly as well. But we've also said that e is related to the natural logarithm. That's log base e. So what I've got here is, and in fact they're inverses of each other. So I've got a graph here, and graphically I just want to show you, and this is one of the questions that's on the notes that I give you, so you can fill this in. But I just want to have a look at the graph of both e to the x and ln x and show how they're related. So e to the x is a really easy one for me to sketch in. I'll just draw this in now. Remember, it's asymptotic down this side, and it's going to look something like this. So this is y equals e to the x. Now, if you have a function and you want to know what its inverse looks like graphically, then all we need to do is reflect it in the line y equals x. So I'm going to put it in here. I'm going to just roughly draw in this line as a dotted line here, the line y equals x. I'll just write that there, that's the line y equals x. And if you look at this and imagine reflecting it, it's going to clearly go through 1 again here, as e to x goes through 1, ln x will go through here, and it reflects like this. It's going to be asymptotic down this side, and then it's going to come up, and it's going to look like this. So what we have here is y equals ln x. So we've got our two graphs now that we can look at. Sorry, that's it would be better if I could draw it all in one go. But they should be reflections of each other like that. That goes through 0, 1, e to the x, because e to the 0 equals 1. So that means ln x goes through 1, 0, because it's a reflection of each other. The other things that we need to point out when we're looking at these two particular graphs is that e to the x is asymptotic here to the x-axis, whereas ln x is asymptotic to the y-axis. In addition, there are no values down here, or even 0. If I put 0 in here and put ln 0 into my calculator, then I'm going to get math errors. We're going to get undefined on the calculator. Because if I put 0 in and keep going down at 0 until I find a point where the graph of ln x crosses and is equal to 0, because ln x approaches the y-axis but it never actually touches it, there's not a point, there's no solution. I could go down as far as I want, and because it only approaches but never touches it, there's never a solution. So I end up, it's what we call being undefined. We put it in there, there are no solutions of ln 0. Similarly, if I did ln minus 1 in a calculator, so I go to minus 1 on the x and I go all the way down, I'm never going to find a solution. We'll talk about this as well when we're looking at solving equations with e or involving e, because here e to the x never drops below the axis, never drops below the x-axis. So there are no values for which e to the x is going to be negative as a solution, because it always is above the x-axis, so it's always positive. So all I've done so far, we've talked about logarithms. We talked about how useful they can be in solving equations. Remember, we just take logs of both sides. That allows you to bring the power into play, and then we can divide by the logarithm to get the answer. And now we've looked at the graphs. We've said that there is a relationship between e to the x and ln x. In fact, we've gone further than that and said that they are inverses of each other, and we can show them graphically here. We've looked at the graphs. E to the x, like we've seen before, looks like this, and if we reflect it in the line y equals x, then we get its inverse, and so ln x looks like this. So now we've built up some properties. We know what e is, we've got a value for it, we know it's important in what we're doing. So now we're going to start looking at solving some equations that involve e, so that next lesson, and I'm going to go live on the next lesson, we're actually going to look at growth models and questions involving these growth models that involve e to the x, and we'll have the skills available to be able to solve these models as well, the algebraic techniques that we need to solve them. So we're going to have a look at a few problems involving e to the x. It won't be a very long video now, but before I do that, we're going to use this property. This is important. This is why these little bits here are the reasons why it's useful to take natural logarithms of both sides, for example, or take e's of both sides. As you'll see, I'll do both, depending upon what scenario you've got. And that's because they simplify down quite easy. ln e to the x and e to the ln x are both just equal to x. Now I'm going to show you that. This one is really easy to show. I'll do it over here. That's because imagine we've got ln e to the x as our starting point. Then the power rule allows you to bring the power down in front. So that's just equal to x ln e. And on the previous video, ln e is log base e answer e. That's just equal to 1. We've said this one already. So this is just x times 1, which is just x. So you can see that ln e to the x, quite quickly bringing the power down, and ln e's 1 is just equal to x. That's an easy one. What about this one here? E to the ln x. We're saying that's also equal to x. Well, I'm going to just show you the steps, because we've done enough now that you can see why this is also true, why e to the ln x is also equal to x. So if I let y be equal to e to the ln x, and then, as we've done before, I'm going to take logs of both sides, but I'm going to take natural logarithms because I'm involving e. So I'm going to say ln y equals ln e to the ln x. It's still in balance. Now at this point I can use the power rule to bring ln x in front. So we get ln y equals ln x times ln e. But we know that, as over here, ln e is just equal to 1. So if that's equal to 1, what we get out is ln y equals ln x. And like before, as long as the logarithm is the same, so when we come to take logs of both sides, we always take the same logarithm. But if ln y is equal to ln e to the ln x, then it must be the case that y is equal to e to the ln x. Here, we can just undo that. If ln y is equal to ln x, then it must be the case that y is equal to x. And if we look back at our argument now, we started off that y is e to the ln x, and with a little bit of algebra we showed that y is also equal to x. So if y is equal to both e to the ln x and it's equal to x, then it follows, therefore, that e to the ln x is just equal to x. So there's two things that we need to take out when we're solving equations involving e's. There's two things that we're going to take out from this. One, ln e to the x is just x, and two, e to the ln x is just x. These are two key points that we use when solving an equation involving e, which is why, you know, the strength of using the natural logarithm here, it's simplified down just to x. You'll see how it works. So there's 5 questions in the notes that I just want to go through, and then we're done for today's video, and you'll be able to do the work on exercise 14G. Right, let's go through them, and I'll show you how we solve them step by step. E to the x equals 4. An easy bog standard equation to work with. The way we do or solve equations involving e is I'm going to take logs of both sides, but I'm going to take natural logs. So I'm going to go ln e to the x equals ln 4. I've just took logs of both sides. The x can come down in front, so we get x ln e equals ln 4. But actually, ln e is 1, so what you get is x equals ln 4. What you could do is this line here doesn't need to be there. We could just say, well, e to the x equals 4. I can see it's involving e, so I'm going to take natural logs of both sides to get this. And then I know from here that ln e to the x is just equal to x. So I could have just gone straight from there and just put x equals ln 4. And I'm done. ln 4 is a number you could get from your calculator, but I'm going to leave it in exact form. B, second one in our notes is 2 ln x equals 7. Now there are 2 ways we can solve this. As when we're solving normal algebraic equations, then we can go through a series of steps to get to the answer. Here I'll show you 2 different ways that you could solve it, and because it gives me a point to illustrate as well. The first one's fairly straightforward. I'm just going to divide both sides by 2. So I get ln x equals 7 over 2. And then at this point, because I've got an equation involving the natural logarithm, so instead of taking logs of both sides, I'm going to take e's of both sides. In fact, I'm going to raise each side to the power e. So I'm going to go e to the ln x is e to the 7 over 2. If you notice, I've done the same thing to both sides. I've given that a base e, and I've given that a base e. Yeah, as long as I do the same to both sides of my equation, it's a legal move. And now, if we look over here, e to the ln x is just x. So I can just write, instead of e to the ln x, I can just write x equals e to the 7 over 2. There's my answer. Another way I could go about this, so let's just draw this in. I start with 2 ln x equals 7. Right, at this point, I could bring the 2 up as a power. So I could write ln x with a little 2 there, so it's ln x squared equals 7. All I've done at the moment is used the power rule of logs, almost like backwards, bringing it up as a power. Now I take e's of both sides. So I go e to the ln x squared equals e to the 7. Now before, I said that e to the ln x is equal to x. But this can be this doesn't have to be just x, it could be x squared, x cubed. So e to the ln x squared, instead of just getting x like with the previous example, when I had e to the ln x, what I get out is x squared equals e to the 7. And then at this point, I take the square root. And the square root is the same as a power of half. So if you imagine multiplying this by a power of half, I get x equals e to the 7 over 2. So it still comes out. This is obviously the easiest way to go about it. So we just divide by 2, take e's of both sides, and the answer comes out. The reason I wanted to demonstrate this, I mean at this point here, when you take the square root, when we do the square root of certain functions, we normally put a plus minus in front. But if you remember, if you look up here, when we're dealing with things like e, it's only positive. Yeah, it's only true for positive values. Therefore, we can ignore the negative that's on there, and we'll do that where we find another solution later on, because e cannot be negative at any point, it never drops below it. So that's why we don't really worry about using or thinking about the negative,